Sound check. So I hope you can hear me well. Welcome one more time. So I'm glad to be here. My name is Dmitry Korobchenko. I'm from the company called NVIDIA. Probably somebody of you heard about it. So if you think that NVIDIA is the company who can just manufacture graphical cards, that's not true. We also do some heavy deep learning engineering and research. So today I'm going to be talking about one of our tools. It's called NVIDIA TensorRT. So probably you've heard about things like neural networks, and in neural networks we have such thing as inference. The inference is when you apply your neural network in production and you run it in production, and this stage is called inference. And you want your neural networks to work really fast. So we designed this library called TensorRT to optimize the performance of your neural networks. So let's start with our agenda. First of all, I will introduce an overview of convolutional neural networks. You may ask, so why should I talk about convolutional neural networks? Because I'm here to tell you about some tool for optimization. Well, the reason is, in the second part, I'll show you some demo. And in this demo, I will show you how to apply TensorRT to some particular network. And I will use convolutional neural network. So I want to be on the same level with you. So I'll briefly introduce what a convolutional neural network is, just in case if you're not familiar with that. Probably you've worked with some other types of networks, maybe text or just plain vanilla fully connected neural networks. So just to be on the same level, because we will be using some features from that particular type of neural networks. So okay, CNNs. Next thing, I will show you what the TensorRT library is, what kind of features does it have, and what can it do, etc., etc. And second part, I'll show you the demo. Well, in this demo, I'll show you the full pipeline, starting from training. I will show you how to train a model, a CNN model in TensorFlow. And then I will show you in the next step how to optimize or how to port your neural network to production using the NVIDIA TensorRT library. And we will see how it boosts our performance. Okay, so let's start in brief introduction in neural networks, convolutional networks. So I hope that you are familiar with this concept. A neural network, it's some graph which do some calculations. It has some input vector, some output vector. For example, we can predict some values with some given inputs. So we have some neurons. We have some weights corresponding to some connections of neurons. So very simple thing, yeah? But what if we want to recognize cats on images? In this case, such architecture will not work because of many reasons, but one of the reasons is overfitting. So we need to apply something different for this kind of tasks. So what can we do here? Well, in computer vision, by the way, this task of image analysis and image recognition in general is called computer vision. So in computer vision, people usually use such things called features. So feature is a local description of your image or your other type of your data. So in computer vision, people usually use some special types of features. For example, some local features of your image, like edges or something else. And when you extract those features, you can then apply some other algorithm of machine learning, like a simple neural net or something else. But the features are important. So how can we extract features from images? There are tons of ways, but one of the ways is to apply a convolutional operator. So for those of you who are not familiar, very briefly, what's a convolution? You have your image and you have this little pattern on the left here, and we want to find where on our image this pattern occurs. So we just put it on our image and in sliding fashion try to find where this pattern matches to the portion of the image. So for example, we're starting with the left up corner, and then we slide. And at each location, we check whether this pattern is similar to the patch on the image. And we output, and we write the output to our output map, a sort of correlation. How similar is this patch to the corresponding image? So this is kind of a feature map, And okay, so what can we do with neural networks here? Well, it turns out that this convolutional operation is a linear operation. That's why we can express the same operation in terms of neural networks. We can use convolutional operator as a special type of neural network layer. And here we have some feature extractor, but since this convolutional kernel is weights of our neural network, now we have trainable features. So we can adjust those kernels, convolutional kernels, in the best optimal way so that the feature extraction is optimal during the training procedure. And so we have trainable features, then we can apply some other type of neural network and get the result, right? Actually wrong, because this kind of architecture is still not enough. We need to go deeper. What we mean by going deeper, that means that we need to extract not one level of features, but multiple layers or levels of features, or in other way extract hierarchical features. So for example, we start with simple edges, then go to combinations of different edges, and then go to more sophisticated features and objects. And this could be implemented via deep neural networks when we stack together multiple convolutional layers. And this is already working architecture, but let's look a bit closer. So in convolutional neural networks, we of course have convolutional layers, as I already told you. But in more general case, when we have several feature maps as input, we can apply a number of convolutional kernels and get several feature maps as output. And don't forget to apply this very important activation function. It's sort of a non-linear function, which is very important in deep learning, because if you don't apply it, stack of linear layers will give you a big linear operation, which is not very expressive in terms of recognition. So we need to apply some non-linear function in between the layers. Okay, the very useful layer. Another type of layers is pooling layer, which we'll be using, also be using in the demo. This type of layer just shrinks or downscales your feature maps in the spatial dimension. This is used to provide sort of invariance in terms of small shifts and rotations. And also at this stage we can filter out some unnecessary information. For example, we want to recognize cats and we don't want to know what's the pose of the cat was. We just want to know that this is the cat or not. So at this stage we can filter out unnecessary information and propagate further only the important information. So that's a pooling layer. And of course we can't build good neural network without this very simple fully connected layer, which just connects all the neurons in the input layer, in the input to all neurons in the output. And this is just a type of layer which is applied usually in the end of your neural network. So if we stack all together, usually people interleave convolutional, pooling, and then a set of fully connected layers. And this is really working architecture, and we will use very similar type of architectures in the end. But that's not the end. What else do we have? Well, the question is, what kind of activation function, what kind of nonlinear function can we use? There are different types of linear function, but the most popular is a rectifier linear unit. This is the graph of it in the bottom. And also there are some other features used in training of neural networks. First of which is batch normalization. Batch normalization is sort of a thing, normalization of feature maps, which is used for better convergence of our networks. And another thing is regularization. We want to fight with overfitting. We want our model to work properly in production on new data. So this is called, when the model works badly in production, this is called overfitting, because, well, it overfits on your training data. So to fight with that, we use two things. Dropout, it's a random cutting out, a random cut of some neurons, random zeroing of some neurons. And weight decay, it's just a L2 regularization on your parameters, on your weights. So we will use all of that in our demo. And the final thing what I wanted to talk in the theory part is how to do training. So in training of neural networks, we use a so-called procedure stochastic gradient descent. We have a data set of, for example, our images and correct answers. So we want to recognize cats, for example, from dogs. And we have this data set. This learning is called supervised learning when we know the correct answers. And we start showing our network the examples with correct answers one by one. And for example, in some iteration, we have some example or sample. We pass the image through our neural network and get some prediction. But this prediction could be wrong, and we know the correct answer. So let's calculate the error. How much have we missed from the correct answer? Knowing the error, we can calculate a so-called vector gradient. And this gradient vector could be used to adjust our parameters, to adjust our weights, to compensate the error on this particular example. And we do it one by one, showing the examples or groups of examples, also called a batch. And this is how training works. And we hope that finally our weights will be trained in such a fashion that it will predict the correct answer at each time. So yeah, enough with theory, let's go to practice. So how can we demonstrate the process of data science? So we have this first training, it's called training. So the first stage is a data scientific stage, when you try to learn your model, try different hyperparameters, model assessment, verification, etc. So very data scientific stuff. And for this particular stage, you will use some of the frameworks. For example, here in the bottom, you'll see like different frameworks like Caffe, TensorFlow, Torch, etc., etc. So some high-level, probably with Python interface frameworks. Those frameworks are really good because they are really flexible. You can express almost everything in terms of these frameworks, and they're really fast because most of the frameworks use this library by NVIDIA called cuDNN. It's a library providing low-level operations such as convolution, matrix multiplication, and something else. So these atomic operations are already implemented in this very efficient CUDA language, and we have already these atomic operations, and those frameworks are just use our implementation of all of that operations. But this is still not the best solution, because frameworks introduce some slowdown because of their flexibility. And you want to deploy then your model after your play with the parameters. For example, you want to deploy it in data center, or put it in some embedded device, or maybe in an autonomous driving machine, something there, and you want it to be very fast. So you don't want it to be very flexible during the production stage. You want it just to be fast because you're finished with your tuning, etc., etc. This is my final model. Please make it as fast as possible. So for that particular case, the second case, the deployment, we have the library called TensorRT. So it's nothing to do with training. It's designed only to optimize your inference performance. You have your trained model, probably in some other framework, and you pass it to TensorRT, which consists of two operations, or two parts. First part is optimizer. So the optimizer runs and optimizes your model and prepares it as a very optimized graph and puts, for example, on your disk drive, and then you can use it later. And after optimization step, so you do optimization only once, and then you use this optimized model in production within our runtime engine. So let's see this in more detail. So first step is optimization. Again, you have training separately from TensorRT. TensorRT nothing to do with training. You have your trained model, and also you have to fix some parameters. For example, you have to fix batch size. The batch is the package of samples which we pass at once during a single inference procedure. And also we can specify the precision. Precision is, for example, it could be floating point 32 bits, floating point 16 bits, or probably integer 8 bits. This kind of precision we need to fix at this stage. So why is this important? Because probably you know that if you want to do something optimal, if you want to optimize things, we need to fix some things. For example, if you do some coding, and when you do some constants in your script or in your C++ code, it's more likely that the compiler will optimize it better if you fix something, if you prohibit some dynamic things. So we fix a lot of things. I will show you in more details later, but here we have some parameters, fix it, then we pass it to the optimizer, and it will output our optimized model, also called plan. So which kind of layers can we use, etc., etc. And then we just serialize the plan on the disk, and then we can use it later. And then in production, we simply load our plan and pass it to the TensorRT runtime engine and just execute inference as usual. We can do it again in some embedded device, in the cloud, or in the car. So mostly we're focusing on these three scenarios. Okay, so how can we import our model to TensorRT? So we have support of these frameworks right from the box. We have a Kafka importer, we have TensorFlow importer, and from the latest version we also have support of this open neural network exchange format called ONNX. And that means that almost every other framework can be now imported to this to TensorRT, because all of that MXNet, PyTorch, Kafka 2 supports ONNX format. That's why you can easily import the model to TensorRT. But in case if you have some other framework or you wrote your own neural network, you can use network definition API. That means just you have to write down, probably in Python or in C++, you should write down your definition of your network by hand. But that's not a problem, actually. You can do that too, in the same way as you write down the definition of your neural network in some other framework like TensorFlow, etc. So for both of these we have C++ and Python interface. I'll show you in the demo the Python interface. It's really simple, just a couple of lines of code. So this is how we import models. Then we have a list of supported layers, almost everything which we need for computer vision, NLP, natural language processing, and other things. Also, if something is missing here, you can implement with your own custom layer. So you can just write down your own implementation of a custom layer. It's better to do it in CUDA language, because if you will do it in not on CUDA, not on GPU, it will be a bottleneck, because all of the other layers will be running on GPU very optimally, but you have to switch back and forth to CPU implementation, etc. So please don't do that. Please use CUDA language to write your custom layers if you have to. So that's also very easy to do. I did it myself. Actually, by the way, I'm not the developer of this library. I'm a user of this library. So I just used all of the same things which I'm trying to talk to today. So it's really simple. Next thing, once we imported our model, we will do some optimization. So TensorRT will do automatically for you some optimization steps. There are a lot of them, but let's focus on three main things. First of all, it will do layer and tensor fusion. Here's the example of unoptimized net, or in other words, unoptimized part of very well-known Google Net Inception network on the left, and on the right we have a graph after TensorRT optimization. So what do we have here? You see on the left here, for example, we have things like these three things like convolution, bias, ReLU. Or in other case, you will have convolution, Bayesian normalization, ReLU. And actually, this is different layers in terms of other frameworks. But in TensorRT, we can merge it together and get a single layer, get a single implementation. It will be really faster than calling several layers one by one. This is called vertical fusion. Another case, we have these three one-by-one convolutions, which have the same input. This is also could be merged in a really wide one-by-one convolution. This is called a horizontal fusion. And we have this really wide one-by-one convolution. And another thing is elimination of concatenation layers. So why should we have this layer separately, where we have just these layers writing in the memory location just for the next layer. So just skip unnecessary layer which doesn't do any calculation. It's just a memory manipulation. So we can optimize that too. And also TensorRT will eliminate some other layers which are not used in your inference. So we'll trace what's the path of your flow and cut out all the layers which are not used. Another thing which is really important is precision calibration or precision reduction. So usually during the training we have this very crazy precision. We use a floating point 32-bit floating point. It provides you very high exponent power, like 10 to 38. You really don't want such big numbers. It's okay if you downgrade to FP16. The precision will be still enough for your classification, regression tasks. It will still work, but you will increase your speed in this case. And if you go further, we can downgrade even to integers, but for this particular case, for integers, you will have to recalibrate your weights. This will be done by TensorRT automatically. You just have to pass. You just have to pass some calibration data set. TensorRT will run inference several times on this calibration data set, and it will see, well, in what range do weights going, and it will recalibrate the weights so that the entire network will be working properly. So yeah, we can reduce the precision, and this will give us really great boost in performance. So, for example, we can compare FP32 and FP16. Also on the latest generation of NVIDIA GPUs, we have such things called tensor cores, and tensor cores are cores on the GPU which run really fast on FP16 mode. So if we reduce to FP16, we'll get much higher speeds. And another thing which is also really important is automatic selection of the best kernels. For example, you have convolutional layers. But there are different ways to implement convolution, via matrix multiplication, via Fourier transform, via Vinograd algorithm, etc. So which one to choose? Well, there are different implementations of different layers. And the TensorRT library will just run each layer on this particular GPU, on these particular parameters, and select the best one. And that's why we need to fix batch size, and we also need to fix input size. So, for example, we're given that our input will be 256 by 256. That means that everything is fixed, and we can run with these particular parameters the inference with different algorithms and see, okay, on layer 1, we will choose the convolution implemented by matrix multiplication. On layer 2, the fastest was Vinograd. Okay, we'll take that, etc. And also, all those kernels are also optimized for different GPUs. For example, TensorRT will see, okay, you're using Jetson TX2, okay, that's why I'll use this particular kernel, etc. So at this stage, the most optimal kernels will be used. And again, performance will be boosted in several times when you use TensorRT comparing to other frameworks, even though other frameworks also use QDNN library, which also implements very optimally these kernels like convolution, matrix multiplication, etc. So, but TensorRT will do it even better. And for those of you who were familiar already with TensorRT, just for you, what's new in the latest version 4.0, which released recently? First, support of open neural networks exchange format. Next, support of FP16 in custom layers. That means that you can now write your custom layers and using FP16 there. Previously, you have to use FP32, and that was not so optimal. Next, support of some other new layers and support of new architectures like neural machine translation, speech recognition, and recommender systems. So that's new, but most important is first two things, OpenNNX. That means that you can use a lot of frameworks now to import your models, and FP16 in custom layers. That's it. Now let's run for the demo. So here will be a lot of code. So please fasten your seatbelts, buckle up. Let's go. So first of all, I'll show you how to train your model in TensorFlow. Then I'll show you how to prepare the TensorFlow model for inferencing, but in terms of TensorFlow. So this is called graph freezing. And next, I'll show you how to do the inference in TensorFlow. And that's it with TensorFlow. Now I'll show you, later I'll show you how to transfer your TensorFlow model to TensorRT. It's called optimization. And then I'll show you how to do inference in TensorRT. And finally, as a bonus, I'll show you the latest feature of TensorFlow, where TensorRT is integrated right inside of TensorFlow. So this is TensorRT plus TensorFlow as a bonus. Let's start. TensorFlow training. I will show you some Python code in some Python notebook. So even though there will be a lot of code, just follow the such things like I will just select the most important thing. So here I will describe the model. I'll be using TensorFlow Slim. It's a library within TensorFlow which uses some short, compact description of layers. So nothing too important here, but I will show that for example, for convolutional and fully connected layers, I will use this particular activation function, this particular initializer for weights, this particular regularizer, for example, we will be using L2 regularizer, so this is not really important. And also for convolutional layer, we'll be using batch normalization. As I told you, this is a really helpful technique. So this is kind of things when you, this slim arc scope means that you can apply all of that to all the layers below that. So below that we have this bunch of layers. We have some convolutional layers, conv2D, pooling layers, fully connected layers. So this is our network. It's actually a standard VGG-A network plus batch normalization, for those of you who know what is VGG network. So this is our network, pretty simple, but it's huge actually. It's used for ImageNet classification tasks, so that we will use the same thing, but with batch normalization. Some settings for training, like crop size. We will be cropping our image. Loading rate is the speed, how we apply gradient during gradient descent, and some other stuff, not really important here. We have our tensors called train image and train label. Those are the tensors which we will grab to get our training data one by one, getting a batch of images and batch of correct labels. Then we'll define our net with this line of code. Logits is the output, train image is the input node. Then we will apply our loss function. So in the loss function we will pass our train label, it's the correct answer, and logits is the output of our network. And we will be using softmax cross entropy loss, pretty standard thing. And we have our loss finally. Then some other setup of training parameters. First of all, we'll set the LR is our learning rate. We will be decaying learning rate linearly from learning rate start to 0. Then we will create our optimizer. We will be using momentum optimizer. And finally, we will create this train op. This train op is the node. If we execute it, that means please TensorFlow execute a single iteration of gradient descent. So if we run this operation trains op, that means we run one calculation of gradient and one weights adjustment. And that's it, that's our training loop. So these two lines, 4 iterations, please session.run, meaning execute this train op. And executing train op means one iteration of gradient descent, etc., etc. So just a simple loop. And we started our training. This here I printed the loss values. It's starting to decreasing. We also can look at the same thing in so-called thing as TensorBoard. In TensorBoard, We can see how learning rate decays, how loss decays. We can also check how training graph looks like. Later I'll show you how to see what's inside of those things when we will do optimization. But very useful thing if you're a data scientist, how to check whether it's plotting some graphs or seeing how your graph looks like. Next thing, graph freezing. It's just a standard operation for TensorFlow. First of all, we will create our network one more time from scratch, but in this case we will pass is training equal false. It means that some parameters like batch normalization and other things will be turned into mode, inferencing mode. Yeah, creating our graph, restoring our weights from the training stage. So training outputted some snapshot with weights. Now we restored it, and this is the freezing. What's freezing? First of all, we remove all the training nodes. So things like initialization of weights, saving, etc. So remove everything what we don't need at inference stage. Second, convert all variables to constants. That means that we just fix all the variables as graph nodes. And secondly, we just write it down on our disk. So this is the frozen model. And if we see what's inside the frozen model, we can see that there are only important layers here, nothing else. So our weights, our convolutional operators, batch norm, max pooling, ReLU, only those things which we'll be needing at the inference. And if we see in TensorBoard the same thing, this is our frozen graph. Again, nothing related to training, only inference stuff. But if we zoom in and see what's inside the convolutional layer, we can see that things like convolution, batch normalization, and ReLU are 3 different layers. But as I told you, this is not very optimal, and we will hope that TensorRT will fix that. And how can we do inference in TensorFlow? So very simple. We just import our frozen graph. We will specify which node we want as input node, which node we want as output node, getting them as net int and net out. Load some image. By the way, this image of my mother's cat. So once she told me, so why do you use images from some random cats from internet? Why don't you put image of my own cat there? So here we go. So we load our image and we do this simple inferencing, and that's it, the cat. And the performance is 5 milliseconds on one image. Pretty good, but we can actually increase that. How can we do that? Well, let's run TensorRT optimization. First, engine building. So actually not so important things here, not so much important things here, but the main thing is that we just need to specify the path to our frozen graph. And the second important thing is that we will use data type half. It means FP16, floating point 16. First, and just let's count steps. Step number 1, convert frozen graph to UFF graph. UFF is a sort of intermediate format. So we just load our frozen graph from TensorFlow to a UFF model. Then create a parser for that particular model, and then run the optimization. Again, it's step 3, 1 line of code. You pass all the parameters here, like your model, your parser, max batch size, workspace size, and data type, half. Let's go to the console, to the terminal now, and see what TensorRT outputted. It said that, well, we had 38 layers initially, but after fusion of convolution and batch normalization, we had 30 layers. Then, after fusion this layer with ReLU, we have 20 layers, so we reduced layers from 38 to 20. We have now 20 layers, and that's it. The optimization is done. We just saved it to a file, serialize. That's it. We have first stage done. Now let's see how inference works. Simple enough. Load TensorRT library, and in this case we load the engine from the engine file, from the engine .plan. Here's our engine. Again, load the image, but in this case, it's important that you transpose your image to this format CHV. This means the channel first, channel goes first, and you select your precision, like for example floating point 16 or floating point 32. Again, using the same image, and with one line of code we run the inference. And the same prediction cat, and let's measure the time. Wow, we have 179, and in TensorFlow we had 512. Well, at least in 3 times faster, although the TensorFlow implementation worked on same GPU, with same QDNN layers, etc., etc. Yeah, success. And very briefly, I'll show you the new feature, TensorRT plus TensorFlow. So as I showed you previously in TensorFlow, we had these 3 steps: train model, freeze graph, run inference. But here, currently, you can do the same thing with TensorRT optimization, but inside TensorFlow. You train your model in TensorFlow, you freeze your graph, then you run the optimization step, and then you perform your inference right inside TensorFlow, as you do before in TensorFlow, but with all optimized layers. So currently, now you need to just load the TensorRT from TensorFlow already. You load our frozen graph, which we prepared previously, and then you run the optimization. You pass all those parameters as previously we passed to TensorRT, but currently this is done within TensorFlow. And after the optimization, we will get the same TensorFlow graph, but some of the TensorFlow nodes will be replaced by a single TensorRT optimized node. I'll show you in a minute. Yeah, so here it is. So we have some layers still from TensorFlow, but we have some new layer, TensorRT operation. So in terms of TensorFlow graph, for example, this is not actually a conv and pool, this is some other thing, but important thing here is that in our TensorFlow graph, we have a new operation, TensorRT. And this is a compact representation of some group of layers which are optimized and merged together in a single operation. And for inference, we do the same thing as we did before for the TensorFlow inference. We just load our graph, but for this time it's not the frozen graph, it's a TensorRT graph after the TensorRT optimization part. In the same way, yeah, this is loading the graph session, some usual TensorFlow stuff. Again, this is our cat. And the same thing as we did before, like, again, within TensorFlow, without using TensorRT runtime engine. Within TensorFlow, we use our inferencing, our prediction is cat, and we have, again, improved our performance, because in pure TensorFlow, we have 512. Although you can notice that this is not as good as a pure TensorRT, but this is mostly because we had not all the layers were converted. So we are still working on that to make it even further. Actually, together with Google, with TensorFlow team, we're working on making this even better, but currently, anyway, again, you can use this tool too, right inside TensorFlow. And conclusion. So I hope it's clear now that TensorRT is a very good library which enables significant acceleration of inference procedure. How can we do that? First, we optimize our graph. Second, we automatically select the burst kernels matching your hardware and parameters. And third thing, we can reduce our precision. For example, for FP16, we do not lose any accuracy, we just increase the performance here, especially on Tensor cores on the Volta GPUs. And you can use models from various frameworks like Kafka, TensorFlow, and some other frameworks which support ONNX format. And you can also use your own custom layers. Yep, so that's it, thank you. If you want to see the code which I just showed you, you can go to this GitHub. Actually, this QR code is also about this GitHub. Also, you can download TensorRT from here. By the way, a quick disclaimer about this GitHub code. I haven't updated the code yet, so you will find the old version here, but I will do that probably on Monday. So on Monday we will have on this link everything which I showed you today. TensorRT library. There are tons of examples, samples there. So for each case, for example, I want RNN. There is an example here. I want custom layer. There is an example here. And for those of you who are new to deep learning, we also have this thing called Deep Learning Institute. It's a bunch of courses and labs related to deep learning. That's it. Thank you so much. I think we have some time for questions.
Yes, absolutely. I was just going to mention that we have also 5 minutes for questions, so if there's anything you'd like to ask, please do, but also remember that you can approach Dima personally and ask questions too.
Yep. And you can also ask in Russian if you can.
I'll be the helper for the questions.
Quick one. Do you have demos for PyTorch as well?
I think yes. Yes, we have a demo for converting from PyTorch to TensorRT using ONNX.
Okay.
In this first link.
Because how you deal with dynamic graphs, I suppose?
That's a good question. Of course, not everything is supported. For example, even in TensorFlow, we don't support a lot of operations. You have to do something by yourself. And of course, the dynamic graphs are, well, I'm not sure how dynamic graphs are implemented in ONNX format. I guess that when you compile or save your graph in OpenNX, it's no more longer dynamic.
That's what I would assume. I don't know about PyTorch, but I would assume if we want to use this.
So yeah, forget about dynamic graphs. Everything is static. Even though the input image size is static, no dynamic graphs.
Okay, thank you.